Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to look at chapter 18.7, which is the last official section of chapter 18, although we're going to look at one more that we left for the end from chapter 3. But chapter 18.7 is about infrared spectroscopy. This is going to be an analytical tool that helps us identify organic compounds. So let's take a look at it. So, in infrared spectroscopy, what we are going to be using is what is called a spectrophotometer. Spectrophotometers are tools that we can use in chemistry in order to look at different compounds by essentially bombarding them with electromagnetic radiation of different kinds. In this particular case, because we're looking at infrared spectroscopy, we're going to specifically be looking at bombarding compounds with infrared electromagnetic radiation. The IR radiation in an infrared spectrometer is essentially going to cause the organic molecules to vibrate. Different bonds in organic chemistry, whether that's a carbon-carbon bond, the carbon-carbon double bond, the carbon-oxygen double bond in a carbonyl group, or the OH bond in a hydroxyl alcohol group, are going to have different wavelengths or different what we call resonance frequencies. So essentially, every different bond in an organic compound is going to absorb infrared radiation at a different resonance frequency. That's the frequency where they absorb the radiation, they absorb the energy, and it's going to cause those bonds to vibrate, allowing them to absorb that energy. So when a bond is exposed to a specific wavelength or frequency of infrared radiation, that is its resonance frequency, it absorbs the energy from that wavelength. Infrared spectrums, which is the chart that we get, the graph that we get as a result of infrared spectroscopy, are usually going to use what we call wave numbers as the x-axis. Wave numbers are just a very simple concept. What a wave number is the reciprocal of the wavelength. So it's 1 over the wavelength. So this is 1 over the wavelength, which we say is lambda, if we remember that from honors chemistry. That is going to be the wave number. So essentially, when we look at wave numbers, we are going to look, and if we look right here, what we're going to see is a dip wherever the wave number, let me do a different color here, whatever the wave number of a specific bond is hit, we're going to see a dip in the energy that we're putting into this. So essentially, we bombard our sample with a particular wavelength, and it's holds steady for the most part. And when we hit the resonance frequency of a particular bond in that compound, that is going to absorb the energy. So the energy is going to go down. It's going to dip. So when we look at spectroscopy, we're not looking at peaks. We're actually looking at troughs. We're looking at these deep dips in the spectroscope or the spectrogram. And then as we hit new resonance frequencies, those are going to again dip again as the energy is being absorbed. So we can see these upside down peaks as energy being absorbed in the IR spectroscopy. Let's keep looking. So how are we supposed to read this, right? Because we see those absorptions. We can do one of two things when it comes to infrared spectroscopy. What we can normally do if we had actual, computers and we're in an actual lab, is that we will compare the IR spectra that we get from an unknown compound with a database of IR spectra of a ton of different known compounds in order to identify either the actual compound or at least the functional groups in that compound. We call this process fingerprinting. Because very much like we fingerprint people, when we fingerprint using IR spectroscopy, what we're essentially doing is that we're running an IR spectra for an unknown compound, and then we're just simply comparing that to the IR spectra of a bunch of known compounds, see which one matches. We can also, and this is more what we're going to do in the AICE exam, we can also analyze the spectra in order to identify specific functional groups. So the goal here is not going to be necessarily to identify a molecule, although we can do that given a little more information, but we can actually identify functional groups based on absorption patterns, based on specific things that we know each functional group does. So when we are given in the AICE exam a spectrum, when we're given the IR spectra for something, we're also going to be given this chart right here. This chart is a chart of the different absorption frequencies or resonance frequencies of very specific bonds that are common in organic chemistry. So for example, the carbon-oxygen double bond that we normally see in a carbonyl compound, like an ester, an amide, a ketone, and an aldehyde, are going to have very specific wavelengths or wave numbers they dip at. An amide, for example, will dip around 1640 to 1690. So we'll see in that range a very big dip. Carbonyl and carboxyl carbon double bond oxygen, so ketones, aldehydes, carboxylic acids, are going to dip between 1670 and 1740. And esters are going to dip, or the carbon double bond in an ester is going to dip between 1710 and 1750. Now you can tell that we can actually see that there are overlaps amongst these numbers, right? And there's always going to be overlaps. But for example, if we knew there was a nitrogen in there, it would have to be an amide, because only nitrogens have only amides out of these have nitrogens in them. If we know we had two oxygens, we know it's an ester or a carboxylic acid. So we need more information than just where those absorption ranges are. But they're a really good place to start. To look at another example, if we had something like the OH in a carboxylic acid, a carboxyl group, then that we will see a dip around 2500 to 3000. Whereas if we had the OH in a hydroxyl group, meaning an alcohol, that dip will be higher at 32 to 3600. So we can use this chart along with some common sense and some extra information like the chemical formula to tell what functional groups are in a specific organic compound based on its IR spectrum. So what exactly does an IR spectrum look like? Let's look at IR spectrum here. So this is the IR spectrum of hexanoic acid. In this spectrum, we see that we have a lot of different dips in our IR spectra. One of the things that you're looking for is obviously this is our baseline. So we're ignoring anything up here. And we're looking for, I'll just draw across. We're looking for significant dips. So we have one here where we see a dip around 2971. And that will be the OH here in the spectra. We also see our, where is it? Our CO, so here's another very significant dip at 1721. If we looked at that chart that we had earlier, let me pull that back up, we see that at 1721 is around the area where we get those C double bond O's for esters and carboxylic acids. So we will see that this right here, this in yellow, that 1721 is actually the carbon double bond oxygen, the carbonyl for a carboxylic acid. And we see a lot of this. This can all be attributed to different parts, some of which will be more common in your AICE exam, some of which will not. But for example, we see here at 1419 a dip that is very common of the OH bond as well. And then right next to it, another dip at 1296 of the carbon-oxygen bond in the carboxylic acids. So all of this information combined gives us ideas about what functional groups are in this spectrum. Now, this is something that needs to be practiced in order to be perfected, but there are some common lines of thought or some common similarities amongst AS paper 2 questions. Now, one of the things about IR spectra is not just that we have a dip at that particular wave number. So 1721, again, wave number being the x-axis, 2971 being very common for things like the carbonyl C-double bond O for 1721, the OH for the carboxylic acid at 2500 to 3000, which, 2971 falls right into. It's not just about where in the x-axis these different peaks fall, but it's also about what they look like. So, yes, we look at the x-axis and do notice that the x-axis is inverted, meaning that we start low at 0 on the right side, and then we go towards the left, and it increases towards the left. But we're not just going to be looking at where those peaks fall in this x-axis. We're also going to be looking at their shape, because notice, some of these peaks, very deep, very narrow, very strong. Some of them are much wider and have a lot of little peaks in them. Some of them are much shorter, like this one's right here, that don't go all the way down. And that all tells us different things. When we look at IR spectra, we're in the Cambridge exam, we're not just looking at where things are, although that gives us a good narrowing down because we see the patterns right here, the ranges right here. But we're also looking at their shapes. For example, the carbonyl peak that we talked about is usually very strong and very sharp, meaning it's very deep, it's very narrow, as we saw right here. On the other hand, a carboxylic acid OH is very broad. And we see that right here as well, where this peak, the 2971 peak, is not just a narrow peak, it's a very broad peak. It goes for a long time, it's very wide, versus that deep and strong peak we get for the CO stretch. So that's one of the things that you have to start to realize, is that not just looking at where the peaks are, but what do they look like? Because in reality, in the AICE exam, we are mainly going to deal with just 3 different peaks. And we're going to look at the differences between different spectra to tell whether those peaks are there or not. The absorption range, that number of the x-axis, is not going to be the only thing that we look at. And in fact, you got to be careful with these numbers, because a peak might be slightly above or below these ranges. And a mild peak, yes, should usually be between 1640 and 1690, but there are other stuff that happens in that compound that might skew that one way or the other. So we could have an amide peak at 1620 or at 1710. These numbers are not set in stone. So do use your critical thinking, do use your kind of logic for these type of problems. Don't just look at whether it's within the range or not. So let's look at some examples here, because you will be asked to compare IR spectra a lot. So here we have the IR spectra of 3 different compounds. Ethanol, a 2-carbon alcohol. Ethanoic acid, a 2-carbon carboxylic acid. And ethoethanoate, a 2-carbon ester that has 2 carbons on each side. So for this spectra, the number of carbons obviously is 2 carbons each, except for the ester, which has those extra 2 carbons from the O chain. But if we look at these all have similarities and they have differences. For example, if we look at the carboxylic acid, sorry, not the carboxylic acid, the ethanol, we'll notice that we have the very deep, wide peak all the way to the left in the 3000s. That peak is textbook hydroxyl peak. peak. We're always going to have these very wide OH peaks all the way in the 3000s when we have an OH group. If we notice for the ester, which does not have an OH group, that peak is missing. If we look at the carboxylic acid in the middle, that peak is also there. Notice, are they identical? No. But it's still a wide peak at around 3,000 to 3,500, around there. That is, again, textbook of that OH peak. But we don't only have that, like we do in both of these, because otherwise it will be the same compound, essentially. Notice that we also have this very deep, narrow peak at around 1,700. That is a textbook carbonyl peak, the carbon double oxygen peak. Notice that that peak in the alcohol, which doesn't have the carbonyl group, is completely missing. There is no 1,700 very deep, narrow peak in the alcohol because it doesn't have a carbonyl bond. If we look at the ester, we'll notice that we do have that very deep 1,700 peak, around 1,700. That's very narrow. But what is missing on the ester? There's no broad OH peak on the ester because the ester, unlike the carboxylic acid and alcohol, does not have an OH bond in there. So these three things are, or I really should say two things, are the textbook things that you're going to see on the AICE exam. The main peaks that you're going to be looking at when it comes to paper 2 questions and paper 1 questions. The broad peak in the 3000s for the OHs and the deep peak, very strong deep peak at 1700 for the carbonyl group. And that alone can tell us the difference between different compounds. If I were to ask you to choose one of these three for a carboxylic acid, you would choose the one that has both the broad OH peak and the very deep carbon double oxygen group. But if I asked you to choose one for the ester, then you would just look for one that has the carbonyl peak at 1700, that's very narrow and deep, but no broad peak at 3000 for the OHs. This is a lot of what you get asked on the AICE exam, is to look at these peaks and to essentially compare different spectra, different compounds, and assign them spectra. So it's a kind of mix and match. And we're mainly looking for just these two peaks. Are there possibilities where they could ask you about any of the other peaks on the chart, like the aromatic 1500 to 1680, or the nitrile 2200 to 2250? Again, if you do have a nitrogen, then yeah, you will look at the nitrile, you will look at the amide peak for the carbon double oxygen. But for the most part, in my experience, these are the two peaks that they focus on when it comes to the AICE exam. The carbonyl peak, whether it's there or not, and then the hydroxyl peak, the broad peak at 3000, to see whether the OH is there or not. Well, that's it for this chapter. I will see you all when we look at 18.8, which is technically actually a section from chapter 3 that we skipped when it comes to mass spectra.